Hello, I'd like to present a overview of modeling with SysML, the system modeling language. And this is a set of charts that was originally derived from these two individuals that were very and continue to be instrumental in the development of SysML. And one of them, Sanford, is one of the authors in this textbook here. The main author, Sanford, Freudenthal, as well as Joseph Wolfram, put together this presentation as a part of a training course, and I've adapted it some. I'm going to be using it for a couple classes that I'm teaching. And so this is just a summary of the textbook that we have here, a practical guide to SysML, and currently at the time of this recording, and it's in the third edition. And it is a very comprehensive guide to SysML. And this is getting in the whole area of model-based system engineering. And so if you don't have this textbook, I'd highly recommend it. I think it's quite excellent. And so the SysML, OMG SysML was adopted in 2006. And once again, the last time I checked, its current revision is 1.6. There's a lot of good information that continues to develop to try and create a infrastructure and a way of doing system engineering and system engineering with this type of approach. So this is what we'll be covering in here. There is a whole course that this is a summary of, and so this will just be trying to give some introduction of the high points. And I will be walking through some of the common SysML diagrams. And hopefully as a result of this, you'll become a little bit more proficient on what it is and then how to be using it. So this was originally a course to try and give a tutorial into model-based system engineering and giving people some familiarity with SysML. And what we'll start to see is that SysML derived out of UML, and you'll see that there are some common diagrams that are between those two. So in the past, the system engineering was done in a very different way. And so it was very much document centered. And now we're moving in this direction of model centric. And this has been a gradual development for quite some time. And so we can have a much more dynamic and interactive and adaptive way of looking at system engineering as a result of this process. So in terms of model-based system engineering, what it does is it formalizes the practice of systems development through the use of models. And so models is used all the way through the process. And I've heard that the term a digital twin is something that's starting to be used in terms of as you develop a design, you have this model that it grows as you develop the system. So it's broad in scope and integrates with multiple modeling domains across life cycles from systems to components. So the range and applicability is wide. The results in quality / productivity improvements, and it has been demonstrated, and it does lower risk. It provides rigor and precision and communication among the system and project stakeholders, and it also helps with the management of complexity. So in the system development process, there's a lot of different ways that you can be looking at it. So here is an example of a diagram of you can be thinking of integrated product development and how you start from working with the stakeholders, get the requirements, you start to manage the system development and do your planning. And as a result, you define system requirements and design that gets formulated into the actual system and at various levels. And then finally, you have to do the integration and test, and then you're ready to deploy the system. So here is just another way of thinking about that. We can be thinking of the major systems engineering development activities. And so you have the analysis that's done up front that then folds into the the system requirements. You have the logical architecture, and then the synthesis and the allocated architecture. So you come up with an idea. You then have functional decomposition that you define into requirements. You do that, break it down into logical parts, and then you can start to finalize the architecture. So there's a lot of different ways of conceiving this, and this is one way to be thinking about that. Well, where does SysML come into this process? And we'll be seeing this from a couple different points of view, but basically there's 4 different buckets, if you will, that fall into what SysML is trying to do. Requirements. This is something that doesn't exist in UML. So there's that. There's behavior diagrams. There's the structure diagrams, and there's the parametric. And we'll be getting into the more details of each one of these. And so we have activity diagrams, we have block definition diagrams. And so this would be something you would see with structure. You have internal block diagrams, which that gets into more detail. Parametrics, which talks about the physics and how things relate to one another. And you can see how there's these arrows and dotted lines relationships. This is where the power starts to come in with SysML. I like to think of that you're creating a database, and there's relationships among various entities that you can be playing out, and you can have rendering of that through some of these diagrams. What the power is, there is that backplane of a database. And so here is another way of looking at the SysML diagrams of the 9 different types. And so you have the behavior, the requirements, and the structure. And sometimes the parametric can be viewed as a separate category, as we were showing in this diagram. This is a version that I came up with that's just shows that how this parametric can be considered either part of the structure or as a separate 4th category. And the behavior diagram, there's a lot of different types of diagrams there, and we'll be walking through that. And really important in the design process is the requirements, and there's a couple different ways that you can be using that to capture the details of what you're trying to do with the design. So here are these 4 different categories, and here we're trying to use an example. And so we, at a high level, we can be coming up with the details of a design for an ABS braking system. And so we have the block definition diagram, the internal block diagram of some of these things being mapped out. So that would be number 1. The behavior, and so we have the state machines, we have the activity diagrams, and we have the sequence diagrams that we can start to be fleshing out the details of how it actually is going to behave in various types of scenarios. We have the equations and the specific ways of how things are going to engage. So it takes time, and there's a certain amount of braking force, for example, how much of acceleration is there, and things like that. And then for the requirements, we have what for some might be quite familiar is you have rec IDs, you have the actual text of the requirement, and there's a lot more details that are also can be annotated as how is it going to be verified, and other types of things that can be other fields that can be included with the requirements. So let's continue on with this, what we're trying to cover. So the SysML diagram frames, each SysML diagram must have a diagram frame. And so this is the structure that we've started to see already, is that the best way of using the SysML diagrams is you list the type of diagram type. And so we saw examples here. And this chart where we see these little 3-letter, 2 or 3-letter designation of that's the actual kind of diagram. Then you have a name, and there's different relationships that you have that you can have version control, and there's all kinds of things that you can be using to help you out with this. And just to keep in mind that I did mention that there was this textbook that this is based upon, and a lot of these figures are directly out of that textbook. So I'd recommend that you take the time to look into the practical guide of SysML that I mentioned at the very beginning. All right, well, we'll take a little bit of time, and this will be the majority of this presentation. We'll walk through those diagrams one at a time. And so here are those 9 again, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have the package diagram. And so the package diagram represents the organization of a model in terms of packages that contain modeling elements. And so how do you start to be thinking, say, for an automobile, how do you bin that into various categories? You can have the actual details of the design. You can have the details of the testing. You can have the details of other kinds of how it actually is going to be used operationally. And so you can be using this kind of approach. And so here we can have the overall automobile model, and these things can be feeding into that. And there can be tons of details that could be either annotated in this diagram, or as in this case, we're just showing a top level, just trying to give an organizational structure. So a requirements diagram, this represents text-based requirements, and this is important, and their relationship with other requirements, design elements, and test cases to support the requirements traceability. And as you're building out these diagrams, you can be including and showing specifically how the requirements ties into other parts of the design. And so here we're once again using the automobile example. We're starting to flesh that out into the various categories. Once again, just for illustration, this is still high level, and we're not showing the details of the text in most of these cases. But here we have a few examples where we have the rec ID numbers and the actual text of the requirements. So we can have traceability. And so this is the kind of things that you can have. You can have verify, satisfy, refines. And so we can see in a pictorial fashion various levels of requirements that are laid out and then are linked with one another in different fashions. And so the different types of links that we can make are starting to be shown here. And that's spelled out in the specification as well as in the textbook. For the block definition diagram, this can be a quite useful diagram. It represents structural elements called blocks and their composition and classifications. And so we have blocks that are then tied into, say, a higher level block. You can have multiple layers of that. You can include individuals and how their relationship is within an automobile, say a driver, passenger, or whatever. And those are things that you can start to lay out. We're still using that automobile analogy as we're walking through these charts. So for the use case, this represents the functionality in terms of how a system or other entities is used by external entities, that is, actors, to accomplish a set of goals. So once again, we have the automobile example, and so we have the driver. The driver drives the vehicle. We have vehicle occupants, and it could be an example. Those would be a passenger, and so they can also have certain types of functionality that they can engage with that vehicle. And so we're trying to capture some of those. And so there could be various scenarios that you might be thinking about depending on how in-depth you want to be modeling your automobile use. This is a fairly high-level example that we're showing here. So now we're showing another example of a block definition diagram, and this is trying to show the vehicle system hierarchy. And so this gets into the elements that you have, the body, the chassis, the interior, you have the powertrain, braking, steering, suspension, etc. And here we're showing a more in-depth breakdown of a powertrain. and a little bit more of a breakdown for the chassis. So these are the things that say you might have a top level block diagram, and then you start to flesh out more in details of the train. And because these are all linked in the backend database, these relationships are now present. And this is going to be helping you as you start to do your design and maybe flesh out other things, but you can drill down or go up and show those various types of views. For an internal block diagram, it represents the interconnections and interfaces between the parts of a block. And for design, it is always important to be able to define the interface and talk about specifically what is exchanged at that interface. And so this is where we can start to be fleshing that out in more detail. And so what is the physical environment that an automobile has to operate in? So you have the driver and the vehicle that has to engage with the atmosphere and the road. And so here are some of those details that are being laid out in the internal block diagram. Here's another example for the power subsystem. And we showed this in the block diagram, and now we're showing more specifics here for the power subsystem. And so this is a modern type of system that has a processor in the vehicle that manages transmission control. And then we have the other elements that are relevant. And so we showed other examples of the car in an environment with a driver. And now we're drilling down into more of the specifics for the powertrain. An activity diagram represents behavior in terms of the ordering of actions based on the availability of input, output, and control, and how the actions transforms the inputs to outputs. And so there's things that are done by and then engage with. And so we're showing some examples here. So here we're showing an interaction between a driver and a vehicle. So the driver controls the acceleration position. And as a result, the vehicle responds by providing the power. And that power then goes into the drivetrain that helps for the car to go forward as requested. We have a start, and then we have an end state here as well. And so when the car is turned off, it goes into an inactive state, is what we're trying to show. For an activity diagram, here is an example just going through the various elements of providing power. So you need to have fuel before you can have power. The fuel goes to the engine. Then the engine is converts that fuel into energy. That energy is put into the transmission. The torque is applied. And then that in the transmission and in the differential, the torque is distributed to the wheels. And so you can see here, we're showing an example where it is passed on to the left rear wheel and the right rear wheel. And those are finally given the torque to move the car forward. And so here we're showing the different players, if you will, and how it ends up as the final result for accomplishing the movement of the automobile. So for a sequence diagram, it represents a behavior in terms of a sequence of messages exchanged between parts. And so what information goes back and forth between these various elements. And so the driver starts the vehicle. The driver then has the ability to determine what you're going to do. Are you going to be putting the vehicle into a neutral state, going forward or going into reverse? You can be controlling if you're going to be applying the brake or not, or the direction, and turning off the vehicle. So this is still a relatively high level in terms of the sequence. So there are some other examples that we could go through that get into more specifics, but basically, at least at a high level, we're showing a simple diagram here. Here's something where we get into the the sending out a message and a response. And so the request is to start the vehicle. There's an action, and that the vehicle then responds by turning the vehicle on. Once this initial key action and the right other conditions, that it's in park, maybe some other safety features to ensure before the vehicle turns on. But you can put a lot more details, and that's commonly the case. A state machine is another diagram that's quite useful in terms of you're trying to capture how you go from one state to another. So it represents behavior in an entity in terms of its transitions between states triggered by events. And so here we're talking about the drive vehicle states. And so you can have the turning the vehicle on. And once the vehicle is turned on, the ignition starts the vehicle. And then we can be going to these various modes. You can either be in neutral, you can be in forward, or you can be in reverse. And then finally, the exit state is you can turn the vehicle off. Then you no longer can go into these states. So you return back to this vehicle off state. So turning on, you have access to these, turning it off, and then you've terminated. You've gone into a final state that you can't return from. So the parametric diagram, it represents constraints on property values such as F equals MA. If you're familiar with that equation, it was used to support engineering analysis. And so you can be defining this in a variety of different ways. And so you need to be aware of the gravitational force if you're dealing with mechanics. And so that would be something that you're going to be defining. And so you can have the power train force that you know what the total amount of capability of the engine is. You have to be aware of what the drag force of the road is that you're operating on. And so that would be getting into the selection of tires. If it's raining, then there's special criteria that might take place that the car might be intelligent enough to prevent going into an improper maneuver that you're doing in your car. Controlling the acceleration, there is a limited amount of acceleration that you can have in your car based on the type of engine and fuel injection or whatever that is there. And so here we're just laying that out into this vehicle acceleration analysis model. And that's would be all the types of details that are captured in the parametric diagram. So let's continue on as we're walking through these. So you can have an integrated development environment for a SysML model. And so this is just an example of one that you might have enterprise architect, but they typically have this kind of an approach that you can see over here on the far left. This is a project browser. And so you can be looking at the things that you've accessed, that you've created. And so this is what I like to think of as your database. You then, in terms of your drawing, you have the various players and connections that you can be applying towards a drawing. So if you're in the creation mode. And so here we're showing an example of one of those diagrams. This is a use case example that's shown in this illustration. So we'll just move on here. We tried to give a high-level overview of each of the major diagrams that are involved in SysML. And so there's more details that we can talk about the structure of the language, and that's what we'll start to get into here. So packages are used to organize the model. And so models can be organized in multiple ways. And so you can have a system hierarchy. You can be organizing them by diagram kind, or you can be using a viewpoints to augment model organization. These are all the kind of things that an architect can be deciding as they're developing and refining a model. So I showed this example already. So this is a package diagram for an automobile model. Here's an example diagram that we're dealing with the containment relationships. And so this is the crosshair pointing to the parent package. And so we're seeing this kind of relationship. So package contains within a package, that's another possibility. So you can have multiple layers of containment with your packaging diagrams. Here is just an example of package organization for a parking garage gate. And so this could be something that might be of use for trying to play that out. So packages are used for model organization. Package diagrams are used to depict how the model is organized. And the models may be organized using a variety of methods. So let's dig a little bit more in depth into capturing requirements in the model, because this is typically an extremely important part of what you do in designing a system, because you can't design a system if you don't know what you're designing to, and thus the requirements are important. So we have something called the requirement stereotype. It represents a test-based requirement and includes an ID, a rec ID, like the requirement ID, and text properties. It can add user-defined properties such as verification. It can user-defined requirement categories, as if it's a functional, an interface, a performance requirement, or whatever. You can be putting in things like how it is satisfied. And you can also have a requirement hierarchy that is also included. We showed this already, but here is just an example of a automobile specification requirement diagram. And we're starting to show some layers of how that works. You have an overall specification, so you would have maybe some general high-level type of requirements, and then you flow down into more specific areas, and you can be drilling down further than that if you would like. We can have the requirement traceability. We also showed this. So this is just another reminder of some of the details going into what is within the toolbox of fleshing out requirements traceability. So there's 3 ways to depict requirements relationship in SysML. You can either have a direct method, you can either have a compartment method, or you can have a call-out method. So for the direct notation, this is used when the requirements and the related model element appear on the same diagram. So it establishes the dependency of model elements to requirements in the model. So we can read the figure below as the camera satisfies a sensor decision requirement. So that's what we're showing here with the satisfier that we're putting on this line for that connection. For compartment notation, this is used when the requirement and model elements do not appear in the same diagram. And so these are the things that you can start to be fleshing out, that in the database, this relationship is clearly defined. But if you want to annotate or show this specific requirement, the sensor decision, you can be having this one area that will get more specific about how it is satisfied by. So that's the second way that you can have the requirement notation. And a third thing is you can have a call-out notation. This is used when the requirements in the model do not appear on the same diagram. So it uses a note box rather than the model element. This can be used when the model element or tool does not support the compartments. So for depicting the rationale, this is used to explain or justify a requirement or requirement relationship. And so here, these are just more example. We can see the rationale that can be tied in. And so in terms of just having a document, we can see how we can be having a lot more insight, and rather than just having a quote flat file, that we're having all this details and specific relationships that we can call upon. You can also have a tabular format of requirements and their relationships. And so this would be more closely aligned to what one might be familiar with if you had a standard document that's trying to capture the various requirements of a system. And this is the parking garage requirements model that we spoke about earlier. And so this is just showing from a requirements point of view, various categories of the things that we want to be capturing. So the operational constraints, say fee notification, and a lot of other things that we have listed here in this diagram. So in summary, the requirements modeling graphically depicts the hierarchy between the requirements, the traceability between requirements and the rest of the model elements. There are three types of notations used to depict requirement relationships, direct, compartment, and callout. And there are several types of requirement relationships in SysML. And so these are the things that you can be having: containment, satisfy, verify, derive, refine, trace, and copy. So moving on, let's talk about use cases in more detail. So this provides a means for describing basic functionality in terms of usages and goals of the system by actors. Common functionality can be factored out via the include and extend relationships, and it can be elaborated via other behavioral representations to describe detailed scenarios. And so this is the same as what you have in UML. So that's a good thing. So we showed this earlier. So here we're just trying to give a general use case of the operation from a vehicle and occupant point of view at a high level, the kind of relationships that exist. So use case diagrams are comprised of the following: subjects, actors, the specific of the use case scenario, and then showing the relationships. So here is an example of a surveillance system. And so you have an operator that is engaging with the monitoring system. There's also an emergency services if something does take place. And here is an example that we're looking to see if there is an intruder. So there needs to be at least one operator that's monitoring the environment. And what we would hope for is there's a zero number of intruders, but there's zero or more intruders that would actually be engaged. And so we're capturing those details in this diagram. So the subject provides a functionality in support of the use cases. It represents a system being developed. It's also called the system under consideration, and it is represented by a rectangle on the use case diagram. The actors, these are used to represent something that uses the system that are not part of the system. So they're outside of the system box. Can be a person or another system. It is usually depicted by a stick figure and or a block with an actor label. And so then the name, the actor based on the role that they perform as a user of the system. So for the use case, this getting into the actual system, it represents the goals that a system must support. It depicts by an oval with the use case name inside. The name should consist of a verb and a noun that describes the function of the system. So for the relationships of a use case diagram, the relationships, it shows the relationships between the actors and the use cases. The relationships between the use cases that we can have include, extend, and classification. And so we're showing some examples of that in this more detailed use case diagram. For the relationships between the use cases, they include, this depicts shared or reused functionality. The extend depicts optional functionality. It's performed when a particular condition is met. And the classification indicates that the specialized use case inherits functionality from the general use case. So here's just another example of the use case model for the parking garage gate. And so you have a couple different engagers, the driver, and you have the maintainer. And so if the driver pays the bill, they're going to be able to open the gate, or they have the ability to cancel the transaction. And the maintainer has a variety of different capabilities that they can provide. So finishing up with the use case, the use case captures the functionality of a system must provide to achieve the user goals. The use case diagram is made up of a subject, actor, use cases, and relationships. And use case can be elaborated through activity diagrams, sequence diagrams, and state machine diagrams. So we can see how there's relationships between the various types of diagrams that we have in SysML. Okay, now let's talk in more detail about the block diagrams. So that will be the next thing we have here, the block definition diagrams. So blocks are the basic structural elements that provides a unifying concept for describing the structure of an entity. So we have system, we have hardware, software, data, procedure, facility, and persons. These are all the things that we can have. And we have the top level name, and then we have these other compartment level things that are below that. So there's multiple standard compartments that can describe the block characteristics, the properties, the operation, the constraints, the allocations, the requirements, and other user-defined compartments. So there can be a lot of things that can be included in each one of those blocks, especially as you start to develop those connections between various elements. And so here we have a structure for an automobile domain. And so we're starting to map this out, that we have the overall automobile domain. And so we have a specific vehicle, we have the environment, and we have the baggage and as well as the passengers. And then we have this ability to include more details down here, as we're showing here some examples of values. That's one of many types of fields that you can have that would be included in a block. This is giving you an example of a vehicle system hierarchy. We showed this already, and then we have more definition that is put into the powertrain subsystem. So the purpose of a block definition diagram is to depicting relationships between the blocks. We can have either composite association or generalization. It depicts structural features of blocks. We can have part properties, value properties. We can define ports, how things flow in and flow out. And we can also depict behavior characteristics of the blocks. So that gets into operations. For composite associations, it depicts parts that make up the whole, black diamonds on the whole end, and the role name can appear on the part end. So here we're seeing some of those types of designations, the role names, and then the fact that we have a solid diamond, that is another important thing to remember. We can also have generalization. Block definition diagrams can be used to depict generalization and specialization relationships. It facilitates reuse of the specialized blocks. The subclass inherits the features of a generalized block, a superclass, and adds its own features. And so here is something that is maybe familiar for those that have done some programming. And so you have class and say a superclass that uses things that you've already defined. And so it depicts and is a relationship and depicts with a closed arrowhead point towards the generalized block. Value properties, this is used to model quantifiable block characteristics or attributes. It's based on value type, which describes the value for quantities. It's listed in compartments using the following syntax: the value property name, colon, value property value property name, value type name. The value properties can have default values and can also define a probability distribution for their values. Ports, they specify the interaction points on blocks. And there's various kinds of ports. You can have a flow port or a standard port. And so here's just an example of flow ports. It can be used to describe an interaction point for items flowing in or out of a block. And so you can have a quote atomic port or a non-atomic port, and it's depicted as a block on the block border. So those are some more details that are being fleshed out. For standard ports and interfaces, standard ports depict interfaces that specify the behavior feature that is services that a block either provides or requires. A provided interface specifies operations that a block provides. And then we have a required interface that specifies operations required by the block. And it's depicted by a socket. The provides interface is depicted by a ball. So here we have a socket, here we have a ball. And so we can see how those are laid out in the block definition diagram. For operations, operations describes something that a block can do. Operations can have parameters that are passed into or out of the operation. Operations are typically synchronous, and operations are listed in the operations compartment of a block as follows: operator name, open parentheses, parameter list, close parentheses, colon, return type. Here is a top-level block definition diagram for a parking garage gate domain. And so we've seen this in a couple other SysML diagrams. And so here is what we would be capturing with a block definition diagram. Here is another one for the block definition diagram for a gate system. And here is an example of a generalization specialization relationship. So a credit card reader or a ticket reader are more specifics examples of a magnetic strip reader for a more specific application. So to summarize, a block is the basic structure element used to model the system structure. Block definition diagrams are used to depict definition of blocks and how blocks relate to each other. Block structure characteristics include part properties, value properties, and ports. Block functional characteristics include operations and receptions, and block relationships include associations and generalizations. Okay, well, let's get into the next one. Let's talk about the internal block definition diagram here, getting into connections. And so we then start to be thinking about block definition versus usage. And so here we have the block definition diagram, and here we have the internal block diagram where we're talking about the flow of information. So traction detection would then flow into the brake modulator. So the internal block diagram is used as part is the usage of a block in the context of a composition block. You can also be thinking about it in terms of a role. So we have various things in an internal block diagram. We have the enclosing block. So we have the connector, we have the flow item, we have the actual port, and we have the part. So this is just a breakout of what we saw in the last chart in more detail, giving you some more specifics. So here is the vehicle system context showing the external interfaces. We showed this already, so this is just maybe a reminder. And so you have the driver and the vehicle, and the physical environment as we have the atmosphere and the road conditions. And so the driver and the vehicle have to be engaging, and there's interfaces between those that are laid out here for this model. We also showed this before already, so this is getting into more details for a power subsystem internal block diagram and the relationships of various elements. We had a sequence diagram that showed some of these things from a temporal point of view, but this is just trying to show a connectivity interfaces, showing it from that point of view. So we can do the modeling of standard ports and their connectors in an IBD. And so the standard ports specify interactions as services. So the required interfaces specifies requests for services, which we see with the socket symbol. So we have sockets, and the provided interface specifies provider services. And so that's what we see with the ball. Here is an internal block diagram for a gate assembly. And so we see that the gate monitor and the sensor, those are all laid out in this diagram. Here we see an example for a control unit. So we have a ticket reader or a credit card reader. Those are both can be fed in. They read information with the magnetic stripe reader that is then passed into a processor. The results can be shown with a display unit or a printer. Maybe you need to have a ticket to get out, and you also get the feedback from a display as you're trying to be getting that payment or other type, or getting your ticket. So to summarize, an internal block diagram is used to depict the internal structure of a block. The frame of an IBD represents the enclosing blocks. And the internal block diagrams depict the use of a block in a specific context, how parts and ports are connected, and what flows between the parts and the ports. The standard ports are used on an IBD to depict interfaces that specify the behavior features that a block either provides or requires. Okay, well, let's now move into behavior. So this is that next major category. And so let's talk about the activity diagram. So activities specifies transformations of inputs to outputs through a controlled sequence of actions. Secondary constructs show responsibilities for the activities using activity partitions. You can think of that in terms of swim lanes and SysML extensions to activities. It supports, provides support for continuous flow modeling and an alignment of activities with enhanced functional flow block diagram. So here is an activity diagram. We showed this already. So we have the relationships of activities between the driver and the vehicle, putting his or her foot on the accelerator. As a result, that produces power, and power then is converted to torque that is can be applied to the wheels. So that's the top level, and here is that activity diagram we showed for the powertrain, showing more specific details, and we're seeing this temporal flow of how that actually takes place. For actions, these describe how activities execute. It's used to model the steps of the activity, accept input and create outputs. We have call actions. It represents the activities that can be further decomposed into other actions, which allows for hierarchical modeling of activities. And so here we have, say, couple options. Say for required input, we thus would have a required output. We have an optional input, and we also have this numbering scheme. So if it's required, there has to be one, and the required output, there is one or perhaps more than one. For an optional input, it could be 0 or say up to 1. And thus the output would either be 0 or up to some unknown number that would be based on the actual realization of a real system. For decomposing the activity diagram with call behavior actions, pins match parameters in number and type. The rank symbol denotes details are depicted on another diagram. So here we're just, we have a blowout for the generate the video output. And so here we're showing the activity diagram flow of that for a high level, and then we break out a certain specific area as we're shown in the bottom part. Here is some nomenclature. So we have the initial node, and that's depicted with a black circle and a line. The final activity node, you have a black circle with a circle around that. We have a flow final node. It terminates a particular sequence of activities and an X in the circle. So those are some things that are useful to be aware of. We then have fork nodes and join nodes, and here is what they look like. So keep that in mind. You will see these in the activity diagrams and other places. We have decision nodes and merge nodes, and so we have diamonds. Decision nodes are one input, multiple output paths. Only one output path is valid based on guard conditions, and the guard must be mutually exclusive. Then we have merge nodes, where multiple inputs and one output flow. So the output flow is triggered upon arrival of any of the input flows. For control flow, it's used to show a sequence of action. It represents a control token, can be depicted with a dashed arrow to distinguish it from object flow. And like object flow, it can be used with forks and joins and decision nodes and merges. We can also have partitions, or you can be thinking that as swim lanes. It allocates actions to an entity responsible for performing the action. And so here we're seeing on the top, we have the security guard, and the bottom we have the company security system. Can be used to specify a function requirement of an actor, component, or part. It can be depicted horizontally or vertically. And so here we're showing it horizontally. You could also have, we saw some examples of that earlier for the flow of a automobile powertrain. We can have it vertical. So either way are things that we can be using that. Here we're showing the primary path, how that flows through from a start to an end. So that is something that we can have. We can also have this annotated with object flow. So we're seeing that with that diagram. Here we're including the partitions. So we see the different individuals or entities that are listed on top here, 4 of them. So a little bit more complication. For decomposition of a calculated fee, an example below shows use of an input and output parameters for the calculated fee activity. The hierarchical relationship of activities and actions, we're seeing that. So let's summarize. For the activity diagrams, they're used to model behavior that specifies a transformation of inputs to outputs through a controlled sequence of actions. Activities can have multiple inputs or outputs called parameters. Activities are made up of actions. Actions consume input tokens and produce output tokens via pins. Inputs and outputs can either be streaming or non-streaming. Object flows are used to depict the flow of object tokens from one action to another. Action using control tokens and call behavior actions can be further decomposed by calling other activities. Partitions are used to assign responsibilities for actions to blocks or parts that the partition represents. Okay, let's now get into behavior with interactions. And so interactions are, we'll talk about sequence diagrams here. Sequence diagrams provide representations of message-based behavior. It represents flow of control, describe the interactions between parts. Sequence diagrams provide mechanisms for representing complex scenarios, reference sequences, and control logic. We showed this already, but here is just an example of a exchange of information between a driver and a vehicle. The driver asked to start the vehicle is then started, and it responds and provides information or to the driver so that the driver knows that the vehicle is on. We already showed this, the driver vehicle sequence diagram, and so this is just more examples of a driving a vehicle. In terms of the components, the sequence diagram can be comprised of the following. It can have lifelines representing a structural element of a system. This depicts time, and also can have messages, asynchronous or synchronous, and reply. And so those are the types of things that we can be starting to annotate in a sequence diagram. Here we're showing the communication for opening of a gate. So we have the processor is given a signal to open the gate. So it's a Boolean true or false, and then it responds that the gate has been opened. And so that's a communication flow between the processor and the gate monitor. So the sequence diagrams are used to depict the interactions between structural elements of a block. Sequence diagrams are composed of lifelines and messages. Lifelines represent the structural elements and depicts time. Messages can either be asynchronous, synchronous, or reply. Messages represent a call for an operation. Combined fragments are used to depict complex interactions and include alternative paths, parallel paths, optional paths, or loops. Reference interactions depict reuse of common interactions. Okay, well, let's continue behavior discussions, and now we'll talk about state machines. These are typically used to represent the life cycle of a block. It supports event-based behavior and is generally asynchronous. It transitions with trigger and guard and actions, the state with entry, exit, and do activity, and can include nested sequences or concurrent states. And it can send and receive signals to communicate between blocks during state transitions. Event types are change event, time event, and signal event. So here's an example. We showed this for the vehicle states. You turn the car on, and once the car is on, we can choose between the states of either being a neutral, going forward, or going in reverse. Once the car is transitioned back to an off state, that's it's a state that without external intervention, it can't go back to the initial state. So for states, let's talk about that in more detail. The states represent a condition in the life of a block. An initial state is represented by a black solid dot, which we see here. And the final state is represented by a bullseye. So a solid dot with a circle around it. Behavior, the types of actions of a state, you can have an entry, an exit, or a do. So an entry is what happens when the state is entered, exit, what happens when the state is exited, and do, what happens while in a state. So those are the three possibilities. For transitions, it's used to show the flow from one state to another. That would be a solid arrow, and it can consist of triggers, guards, and effects. So we're seeing an example of that for a surveillance system. For composite states, this is dealing with the means of depicting the hierarchy of states. Substates, these are states that are unique to another state of an entry. The composite states are depicted by enclosing substates within a state. So here is a state machine diagram for a parking garage gate. So this is one of the examples we've already seen developed. And so we're just seeing a little bit more details and reflecting back on what we've already talked about. So to summarize, state machine diagrams are used to depict how a block changes state. State machines can be comprised of states, transitions, and composite states. States represent a condition in the life of a block. Behaviors are the actions associated with a state. Transitions are used to show how a block changes from one state to another. Transitions can consist of triggers, guards, and effects, and composite states are used to depict the hierarchy of states. Okay, now let's get into this other category, talking about parametrics, getting into the physics. So this is used to express constraints equations between value properties, provides support for engineering analysis, for example, the performance and reliability. It facilitates identification of critical performance properties. Constraints block captures equations. Expression language can be formal, for example, MathML or OCL, or informal. Computational engine is provided by applicable analysis tools and not by SysML. As is typical for doing system engineering, there's usually a lot of different tools that you bring together for the analysis. Parametric diagram represents the usage of the constraints in an analysis context. Binding of constraints parameters to value properties of blocks is what we're trying to do. Moving on, so here's an example. We showed this for the vehicle acceleration analysis, the parametric diagram for that. So you might want to remember, we talked about that a few minutes ago. And so for defining the constraints and constraint blocks, the constraint blocks defines equations so that they may be reused and interconnected. It defines a set of parameters, and it defines an expression that constrains the parameters. So for defining parametric models, the parametric model depicts a network of equations that constrains the properties of blocks. How do they actually operate physically? The properties of the system are bound to the parameters of the analysis equation. You can think of as an example of a common equation as F equals ma. So in the figure, the properties of the vehicle are bound to the parameters of the vehicle used to analyze the vehicle stopping distance. The parametric model thus helps identify the properties of the system that are critical to satisfying the requirements. Here is a parametric diagram for the gate system that we've looked at in a couple different ways. And so here we're showing the operational effectiveness is what we're trying to get into. Measure of effectiveness is what we're getting into. So we have the availability, the ticket processing time, the credit processing time. So these are specific values that feed into that. And so then we have a operational effectiveness function that models what is the actual operations of this system. So to summarize, for the parametric diagrams, it captures the analysis as a network of equations. It helps ensure consistency between the system diagram models and multiple engineering analysis models, and it can help to manage technical performance measures. For the constraint blocks, it defines parameters and constraints equations. It's represented on a block definition diagram. For the constraint property, we have the uses of the constraint blocks, and it's represented on a parametric diagram. Okay, now let's talk about modeling cross-cutting relationships with allocations. So now for allocation relationships, we're mapping between any two named model elements. A named model element is associated to, that is allocated to or allocated from other model elements. So that's what we're trying to think about here in this section. So here we have these allocate relationships, allocated to, allocated from, that we're highlighting in a couple of different types of diagrams: an activity diagram, a block definition diagram, and an internal block internal block definition diagram. You can also have this in a tabular notation. So here we can be showing multiple allocation relationships. It's not specifically prescribed by the SysML specification, and this is useful for concise, compact allocation relationships. Here we're just showing another example, highlighting what it would look like in a tool, and this is for the parking garage gate scenario. This is an important thing to keep remembering is there is this cross-connecting model elements. And so we have these 4 pillars: the structure, the behavior, the requirements, and the parametrics. And this is this interconnection in the backplane of this database of information for this model that we're having. And so it's really nice to have us remember this as we walk through some specific examples. And so this diagram is just trying to highlight that. So we can have like the requirements. And so how do we verify the requirements? We get into a parametric thing listed here. How do we do a satisfy for something that's listed in the requirements? And so here is showing a relationship between an internal block diagram and a requirement. We can have a value that's binding, once again, with something in the internal structure. And so that's bound to a physical quantity that is related. We can have the allocation of things that are in a activity diagram that are then allocated to parts of a structure. So a functional decomposition of what the system is actually designed to do and how you're accomplishing it through your design. So allocations are used to depict mapping of model elements to one another. There are many types of allocations, including behavior, structure, and properties. Allocations allows allocating activities to blocks, allocating requirements to blocks, allocating logical elements to physical elements. Allocation can be represented graphically through a variety of notations, direct, compartment, and callout. Tabular relationships offer a compact representation of multiple allocation relationships. Okay, well, included in these charts is a class example. This is for a dishwasher scenario. I'm not going to go through this, but I'll just quickly just show these, just highlight that chart. Well, let's do a summary for a process. We covered this chart before, but now we're showing some of the diagrams that are related. So for mission analysis, we would be using the block definition diagram. For the designing the system, we would be using the internal block diagrams, the activity diagrams. We would be using the use cases. I'm sorry, for the analysis, we'd also have mission use cases. Then we start to define an architecture. We're going to be using the block definition diagram, the internal block diagram, and the activity diagram. And then when we do the allocation, the synthesized allocated structure, we're going to be doing allocations, and we showed how we could be starting to do that. So that would be for the major system engineering development activities. For the common sub-activities, for the optimize and evaluate alternatives, we get into the parametrics, and we need to be involved with the physics of the system. For doing the requirements management, we need to be using the requirements diagrams and the specification and traceability. And then for the support, validation and verification, we're going to be using, this would be used in test cases and test procedures. And so we would be using the requirements diagram and the various other things of showing the relationships of how we take a requirement and verify that. So requirements diagram would be very key for that. So coming back to that system modeling activities, we're now trying to annotate it with the SysML elements per entity. So for the system architecting model, it provides an integrated framework. And so we're seeing how the system architecture model with SysML is going to be key and part of a larger ecosystem. And so that picture is trying to give that some perspective and a larger context. So we've talked a lot about the various elements of SysML, and we'll just be finishing up here with a few other things, but basically just summarizing here. So we try to give an overview of the tools. We've given an overview of some of the functions, and the overall tool integration. There's other types of things that we can be thinking about, but we can see how SysML places itself as an important area for this overall tool integration and navigating between all of the things that we would want to be doing in system engineering. In terms of exchange mechanisms, one of the common ones that I have been exposed here is as a file-based exchange, XMI. And so you're trying to get to say if you need to be exporting the database that you've created from one tool to another, that is one possible way of doing it. It's always nice as you have a API defined. So that is great. I've also had many situations where I've been forced to have to do this manually, which is, of course, one of the things you want to be avoiding. There are standard XML metadata exchange formats to go from one proprietary tool to another. That can be a little bit challenging, but there are a few options that are available open source for at least part of what you might want to be accomplishing. So I think I'll just skip this one, but there's a variety of different tool selection criteria that you can be using for things that I do in the classes that I teach. I use it's not open source, but there is a community version available. It's called Visual Paradigms. But for an enterprise environment that you're actually going to be using it to be building a system of systems, you're going to have to be thinking about all of these types of factors. Here's just a list of some of those tools that are out there. It's not complete. I need to be updating this explicitly by putting Visual Paradigms here. Modelio is an open source tool that unfortunately has not been updated for over a year, so it is stale. But there are a variety of other things. Enterprise Architect, No Magic. IBM has a variety of products as well, Cameo. And so those are just a few things that you can be thinking of. So to wrap up, model-based system engineering is something that is becoming a reality that is actually being used in industrial development. And so it gives us this full circle and a lot of agility by what you would like to be doing with a design. So it is something well worth taking the time to become familiar with that and using it. We've talked about SysML and have walked through each one of the diagrams. It's an extension beyond UML. It has some things that are specifically that are only in SysML, like the requirements diagram. And so I would recommend that you do take advantage of the resources that are available with this wonderful set of capabilities. And with that, I'm going to end the lecture, and thank you very much for your time.